If you are tuning into this recording, I would encourage you to try this FRQ. All right, so that was 12 minutes and 20 seconds. You would have another, few minutes. How you guys feel on timing? You guys good with the time? Okay, that's the most important thing. First year I taught not this class, but just AP in general. I didn't really know a lot of the AP style of, making sure the time was understood. And so I didn't even ever give them a time limit on anything. Like when they took the test, they just had the whole block and stuff. And then when they took the AP test that year, they came back and a lot of them said they had some time issues. I was like, well, that's something I got to work on then. So that's why your tests in here are timed the way they do, kind of put you on a little time crunch on these FRQs, just to make sure that you guys understand the time allotment. And I'm sure you guys have figured that out. So sometimes you just have to give up on a problem. And I know that kind of goes against everything in your nature, but you have to save some time on problems you might get right versus one that is a little tough. I am pretty sure there has not been a perfect on the BC Calc exam in, oh man, I don't even know how many years. A lot of years. There's not been a perfect. So you can't have perfection on your mind. You have to get as many problems right as you can. So I would encourage you to score these. This is kind of a fun problem just because I thought they were very nice on this one because they tell you F prime, which saves a whole lot of time. If they didn't, you would have to go through and do quotient rule and find the derivative. They were kind of throwing you a bone. And I think they do that to kind of help with the grading on their end too. So there's not a lot of different F primes that they need to grade with. So that's why they did it. But I'll put the answers up. You guys kind of check, see how you did. But tangent line, we need f of 4 and f prime of 4. Find those two things and then do your tangent line equation. Your line doesn't have to be set equal to y. So yours, if you left it in point slope form, that's fine. If you put it in slope intercept form, I don't know why you would, but it's not wrong. You just have to know the equivalent answer. I don't know what that would be. 20/16 plus 4/16 is 24/16. What's that? 12/8? No. 6/4? No. 3/2 would be your y-intercept. If you did put it in slope intercept form. I don't know why you would do that. B. So when you guys are doing relative max and min questions, this is where you find your critical numbers, then you do your sign chart. So anytime you're looking for relative max or min, that's your sign chart. We haven't done a lot of AB stuff in quite a while. And that was part of the reason why I picked this warm up to refresh your memories on a lot of AB skills that we haven't done, which you guys were really good at. But then once you start learning all the BC stuff, it's easy to forget. Your sign charts will never be graded. And that's why they don't put it up here. But I would encourage you to do a sign chart with 2. And then I would plug in 1 for F prime. I'd plug in 3 for F prime and make sure that it changes from positive to negative. So relative maximum. It's saying consider F prime of 2. I wonder if you have to show F prime of 2 equals 0 to even have a chance. I bet you do. I bet if you're verifying that something is a relative max or min, I bet you do have to show that F prime of 2 is 0 for part of the verification. Interesting. C. So critical points. That's where your derivative. So here's the thing. It's where your derivative is 0 or undefined. Make sure it didn't come up on here. But I was reading some posts on that Facebook group I'm a part of. Make sure that you guys remember that critical numbers or critical points have to be in the domain of the original function. They have to exist on the original function. That had nothing to do with this particular problem, but in general, like let's say, for instance, I'm just making this completely up. But let's say F had, some hole like this. Well, if you found F prime is not going to exist here, but it's not a critical number because that's not in the domain of the original function. Just again, something to think about because it had nothing to do with this particular warm-up, but it was on my mind. So -10. If K was -10, then -5 would be a critical point. The last one, a little touch of BC, partial fraction decomposition. This was worth 4 points right here. And I love this process too. I don't know why, but I really enjoy. I don't know if it's like taking the fraction apart that I like undoing it. I don't know, but I find something satisfying about partial fraction decomposition, which sounds weird, but I really do. You do not have to get your answer all the way down to this final line. If it was me, I would just leave the answer like this step right here. Now you might need to know how to get to that last part if it was a multiple choice question, but don't forget plus C inside of there. How are you guys feeling? Good? Feeling good? Okay. All right. You guys at home feeling good? How's Pepper doing? Pepper like that problem?
I think so. He did pretty well on it.
He did. Nice. Nice. Wouldn't that be cool if you could teach a dog calculus?
I don't think my dog.
You can teach them how to like sense if someone's like their blood sugar's low, they can smell guns, they can find drugs. Why can't they do calculus? Maybe it's more likely to train like a gorilla or an ape to do calculus. Do you think that's possible? You think? I don't know. Okay. All right. Well, so today, what we have, like I said, it's 2 more series convergence tests on e-learning Wednesday. Don't let me forget at the end of this class, I already have had a video from last year. It must have fallen on a similar e-learning day, which actually really benefited me because I didn't have to make another video. But so for e-learning, there is a video on there. Just remind me at the end of this class to publish it. That way you can have it at your disposal like now, because your homework tonight is not very lengthy. And that way you can do the e-learning whenever you want. You will have a quiz on Friday. You have a quiz on Friday over all your series stuff. Okay. So last time we talked about the nth term test, and that only tells you if a series will diverge. It doesn't tell you if a series will converge. That's what the nth term test does. Then we did the infinite geometric series test. This one is rather nice, but sometimes you have to do some manipulation to figure out the first term and what R is to then apply it. What's really nice about the geometric series test is it's the only test, well, it's the only type of series where you can find the actual sum using that formula, first term over 1 minus R. It's the only one. All the other ones, we can tell if they converge or diverge, but we can't figure out what the actual sum is. We will get into what's called error bound. Like we'll be able to approximate what the sum might be with a little range of error, but the geometric one is the only one that we can find the exact sum. So that's pretty cool. Today, we are doing the integral test and we are doing the p-series test. The integral test is my least favorite one. It's not bad. I'll tell you why it's my least favorite one, but it's not a bad test. So long as you are good with improper integrals, because that's what we're doing. With the integral test, we're doing improper integrals. The p-series test is the easiest one to do and see. Like there's literally no work to do for the p-series test. Kind of nice. So let's jump to the notes for today on the integral test and the p-series test.
Hey, Mr. G.
Yeah.
The screen's being weird again.
Oh, I think it's your guys' fault. It's only this.
Sorry, I'll get right on that.
Only this class.
Maybe other people just don't want to say anything. Oh, it's better now. I don't know what you just did, but
I didn't do anything. Is it fixed?
Oh no, it just changed to a different frozen screen.
You got my hopes up.
Sorry.
Yeah, you've got a chunk of screen that's just staying frozen no matter what.
You got
Like-
a screen that's frozen. No matter. I'm just joking. I just quit the Elmo software, so let it load up, and then I will. Let's see. Alex, you doing all right at home?
Yeah, I'm doing all right. Just trying to keep up with all my work while being stuck at home.
Did you end up getting it, or are you all good?
Well, about 2 weeks before, well, about a week before my mom got it, I had very similar symptoms, got tested, and it came back negative.
That's good.
And then my test, so I got sick for a while, but with the amount of exposure I've had, I should have some symptoms if I haven't already had it.
Yeah. You sounded like a robot there for a second, like you were a cyborg.
Yeah.
just the way the program. Okay. All right.
but I'm doing okay.
Well, good. That's very good to hear. All right. So the integral test is this. Here's the integral test at the top of your notes. So if you have an infinite series, all right, what we are basically going to do is relate our series to an integral instead. Like a sub n is a sequence where it's just a bunch of discrete values, like 1, 1/2, 1/4, where it's going down by a half each time. It's just discrete values. It's not continuous. What we are going to do is compare that sequence to a function that is continuous instead. Then what we're going to find out is if this integral converges, then that series also converges. The improper integral and the series behave the same way. So we're going to be doing a lot of improper integrals. Now, this is only true if these three conditions are met. All right, so this is kind of why I'm not a fan of this test. I don't mind the integration. I will say when you guys did your improper integral quiz a few classes ago, it was multiple choice, but I was looking at some of your guys' notation and it was brutal. The way you guys tried to notate things and not using the limit notation. I don't know if you did that just because it was multiple choice, the work's not graded. If that's the case, I understand. But on FRQs, make sure you guys are very, very meticulous with how you notate things. I didn't talk about that at the time. I should have, but anyway, here are the three conditions we need to have met in order to use the integral test. In order to even be able to apply the integral test, the function has to be positive. That'd be positive terms. The function has to be continuous, and the function has to be decreasing for some x value. So here's the thing. There's actually some debate between a lot of people. It says these three things have to be true for x greater than or equal to 1. That's not entirely true. These three things just need to be true for some x value and beyond. So like, let's say you have some function that looks like this. You don't need to draw this, but this will come up in a future example. Let's say you had some function that looks like this, where this is 1 right here. Well, this function is not decreasing all the time for x greater than or equal to 1, right? It increases right here. But eventually, like right here, at whatever this x value is, let's say it's 2, eventually this function is decreasing for x greater than or equal to 2. The test can still be applied. So there is some debate between people that write these books and stuff like that. This is not necessarily true. It just has to be true for some x value, okay? So that was something to point out, and that'll come up in an example here later, but I just wanted to address that now. If you are doing a multiple choice thing, then you don't need to state these conditions, obviously. You just apply the test, you do it, and then you get your answer. If you are doing a free response question, you 100% have to say, since f is positive, continuous, and decreasing, the integral test can be used. Like you have to state the conditions that have to be met. Kind of like when we were doing the mean value theorem and the intermediate value theorem first semester, where to use the mean value theorem, the function had to be continuous and differentiable. And you had to state that. You have any theorem you're using, or anytime there are conditions that have to be met, you have to make sure you state that. And so we'll practice that today. All right. So let's do it. First example says, confirm whether the integral test can be applied to this series. Then use the integral test to determine the convergence or divergence of the series. The reason I don't like this test is just because there is so much work involved in these problems. It's not that they are tough. It's just that there's so many places that you can make mistakes. All right, well, the first thing it says is confirm whether the integral test can be applied. Even before that, you know what I would look for? I would always check for the nth term divergence test. Number one, that's the first thing I would look for. So the first thing I would do is just make sure these terms will eventually go to 0. And you can pretty clearly see that they will, because the bottom degree is bigger. You would not need to write this, but just to refresh your memories, I would always make sure that this equals 0, because if the limit of that sequence doesn't equal 0, you automatically know that it diverges. So I would always look for that first and foremost. That could be easily missed. And it's nice if it doesn't equal 0, because then you know it diverges and there's no more work to do. So always look for that. So we need to say that we are comparing this sequence with an actual function. And so what that means is this. We're going to let f of x equal, and instead of having n's here that are discrete values, we're now replacing those n's with x's and having this look like a function instead. So we're going to let f of x equal x over x squared plus 1. And now the rest of the problem is essentially dealing with this function instead of this series with n's and discrete values. We're only focusing on this particular function now. Okay. So to see if the integral test can be used, the first thing we have to say is if the terms are positive. The nice thing about the conditions is there's not a lot of proving that you need to do. You just need to state that f of x is positive, f of x is continuous. We'll talk about the decreasing one here in a second. But this function, f of x, is greater than 0, so they're positive. Is that always true? But when is it true? If x is above what? 0. So we could say for x being greater than 0, I would say for x being greater than 1. If we can use 1, then I would use 1. So I know that this function is positive for every x value greater than or equal to 1. There's no proof to do. You just need to be able to look at it and know. They just want to see, not can you prove these conditions are true necessarily, but do you know what the conditions are? The next thing that has to be true, our function has to be continuous. Well, nothing is going to make this denominator be 0, which means this function is always continuous. So f of x is continuous. And so especially for x greater than or equal to 1. Now, the last one is we need our function to be decreasing for some x value. This is probably the worst part of the problem. But I'm going to do this and then kind of give you guys just a little piece of advice, okay? So the next thing we need to do is show that f is decreasing past some x value. And so this is where we are going to find f prime. We're going to find critical numbers, and we're going to do a sign chart and show that f prime is negative past some particular x value. Okay, so it's not anything hard. It's what we've done for quite a while. We just have to do it. So I'm going to find f prime. We need to verify that this function is decreasing past some x value. So f prime is equal to, and I'm going to go ahead and do quotient rule. Low d high. So x squared plus 1 times 1 minus high d low over low low. I didn't give you a ton of room to work on these notes. I apologize for that. When I created these notes, I did, and then I made the key. I didn't realize how much space was actually needed. So then I'm going to simplify this. So it's going to be negative x squared plus 1 over x squared plus 1 squared. Now wait a second. Then I'm looking for my critical numbers. So I'm looking for what makes f prime 0, what makes it undefined. So I'm going to set this numerator equal to 0. And I'm going to solve this. So subtract 1, divide by negative 1. So x squared equals 1. So x equals plus or minus 1. All I'm really trying to accomplish, understand what I'm trying to accomplish. I'm trying to show that f prime is negative for some x value and beyond. That's what I'm trying to show. And so I'm really just going to put 1 on my sign chart, positive 1. And think about what would the sign of f prime be past 1. So if I plug in any number greater than 1 in for f prime, so plug in 10, I'm going to get a negative on top, a positive on bottom. So f prime is negative for any value greater than 1. What that means is our function is decreasing for x greater than or equal to 1. That was the third condition that needed to be met. We haven't even actually done the integral test yet. Yes.
So since 1 is a critical number, why would we say it's increasing for x greater than or equal to 1?
Because I think 1 would be, because if you're talking about increasing or decreasing, you're talking about on an interval. And so if it starts at 1, then the value after 1 is going to be less than what 1 was. So technically this function is decreasing from 1 and beyond.
Okay.
Does that make sense?
Yeah.
I think if you put greater than 1, you'd still be safe. So here's the thing. Last year, my class asked a whole lot of questions last year. Tons of questions. I was worried I wasn't going to finish the lesson because hands were up. Why this? Why that? And it made me question, think, because I had no idea a lot of their answers or to their questions. One of the questions they had was, is this necessary? Their question was, why does f have to be decreasing? They said, can we just show that f is positive and continuous, then do the integral test and just make our conclusion? And so I put a post on that Facebook group last year, actually went back and looked, and no one gave me a really good answer. And so I actually posted this morning about it. I said, does the function have to be decreasing to use the integral test? And the guy who always is on there answering questions, he said, yes. He said it has to do with, you could have functions that oscillate where, I don't know exactly how he phrased it. What did he say? Bottom line is yes, was you have to show that the function is decreasing. Now, here's the good news. So I've always had my students do this to verify that f is decreasing. What I have been told is, number one, if it's a multiple choice question, you do not need to do any of this stuff. No, that's first and foremost. Number two, if it's an FRQ, they're probably going to tell you in the stem that the function is decreasing. Like they're going to tell you that. You just have to reference it in the conditions of why you can use the integral test. Like this work, you aren't going to have to be doing this work to then do the integral test. Okay. The reason I did it on this particular problem was, number one, to refresh your memories on quotient rule, because it's been a while since we've done that, and doing sign charts and finding intervals of decreasing. So I wanted to practice that one more time. But in all honesty, if you're doing an integral test problem on an FRQ, if you just stated f of x is positive, f of x is continuous, and f of x is decreasing, you'd be fine. Like you wouldn't have to show and do all this proof stuff. Okay. But you do need to state the three conditions. All right. So now I can use the integral test. We haven't even done the test yet. This is just verifying we can use it. Okay. So here's what we're going to do. I'm going to do, instead of the series from 1 to infinity with ends, I'm going to do an improper integral from 1 to infinity with these x's. And basically what the integral test says is, if this integral converges, then that series also converges. If this integral diverges, then the series diverges. They're going to behave the same exact way. Okay. They're going to behave the same exact way. The only time you would use the integral test is obviously if it looks like it can be integrated. Typically, if you see like really quick U substitution in there, that's probably the only time you would be doing this test. Odds are, in all honesty, this is not even going to show up as a multiple choice question, because I haven't seen many of them. But let's do this. Okay. So I'm going to have u be x squared plus 1. I'm going through u substitution, and I can see that u substitution is going to work pretty well, because if u is the denominator, then its derivative shows up in the numerator as x. So du is 2x dx. I'm trying to replace x dx. So I'm going to divide by 2. Okay. Now when I do my replacement stuff, this is where a lot of your notation was pretty gross looking. A lot of you kept the infinity in the integral and just knew I'm going to plug in an infinity. But again, it was a multiple choice question, so I understand that. Just make sure on an FRQ, you don't leave infinity as a limit or as an integral. So we're going to have the limit as b goes to infinity from 1 to b. Here's our notation. Then I am going to plug in my stuff. So I'm going to have, I did this pretty grossly on my actual key. I skipped a lot of stuff. But anyway, I'm going to put the 1/2 out in front. I didn't do this on my key, but I'm going to do this instead. And then it's going to be, oh, I know why I did it. I'll explain it here in a second. So it's going to be 1 over u du. And so this is bad math. Why is this bad math? I understand why I did on my key what I did. Why is this bad? It's wrong. Yeah.
Well, you didn't plug in the 1 to the u.
Yeah, I didn't change my limits of integration. So if you're doing an FRQ, this line is wrong, because these limits initially are x values, and now I've changed to u values here. Does that make sense? So on my key, I'll show you what I did, and then I'll finish. I was curious why I did what I did. So on my key, I knew what the integral was going to be, because this is a pretty easy one to integrate. It's just the natural log of absolute value of u. So it's the natural log of the absolute value of x squared plus 1. So on my key, I never actually put my u expression inside the integral. And I think I did that because I didn't want to change my limits. That saved me having that little error line. So just something to think about. I guess what you could do, what can we do? Here's what we can do. We can change our limits. Let's do it this way. So I'm doing it different than the actual key. So if x is 1, then my u value is 2. So I need to change that lower limit to 2. And if my upper limit is b, if x is b, then b squared plus 1 is my new upper limit. And so if I do it this way, now I never have to go back to the x expression. It's completely up to you. Just make sure you're aware when you have some linkage error stuff. All right. So now I'm going to have 1/2 the limit as b goes to infinity of the natural log of the absolute value of u from 2 to b squared plus 1. And then I can plug in b squared plus 1 for u and 2 for u. Natural log of b squared plus 1, which is always positive, so I don't need the absolute value anymore, minus natural log of 2. And then at this point right here is where now I can, I'll use air quotes here, plug in infinity. And so if I plug in infinity, I can see I'm going to get the natural log of infinity, which is infinity. So basically this is infinity, which means this diverges. Therefore, the series from n equals 1 to infinity of n over n squared plus 1 diverges by the integral test. That's one problem. So it's not hard. Like there's not one thing in that problem we did that was hard. It's just a lot. But again, a time saver would be, you can just say the function is positive, continuous, and decreasing. You do need to make sure you state those conditions or you won't earn your full point. Questions on the integral test? It's exhausting is what it is. Yeah.
Why do we have to write limit instead of just writing natural log of u from 2 to infinity?
They just, in terms of notation, infinity is not an actual number, but you can take the limit of something as something goes to infinity. But infinity is not an actual value that you can ever plug into something. That's why.
Mr. G.
Yeah.
So earlier we did the nth term divergence test, and it says it converges. Is that just saying it could converge or diverge? Like us just checking to make sure we don't know what diverges right off
Just
the bat.
at this part right here, you mean? Yeah. So this, like I said last time, 19 out of 20 times. So if you're given a bunch of series, 19 out of 20 times, this will equal 0. That just tells you you don't know whether it converges or diverges at that point.
Okay.
It's still kind of a coin flip at that point. If this limit equals something other than 0, that's actually what you want to happen. You want that to happen because then you automatically know it diverges. This is what will typically happen, and then you'll have to apply more tests. All right, next one. You know, I found, so being my 3rd year now, I'm starting to see a lot of mistakes students make. One thing I found a lot of my students do with these tests is that you'll be able to use them. You'll be able to tell if it converges or diverges, but I'll have a lot of students that'll write this. Like they'll say this diverges and just completely ignore the series part from n equals 1 to infinity. Make sure you're always including that as part of your like conclusion and in your work and stuff like that. This is not a thing that they would not give you credit because this doesn't diverge. This is nothing. The series diverges. So that's just something. All right. How pretty your sigma is really doesn't matter. Mine's hideous. All right. So now we're talking about this series. The first thing I would check is, does it pass the nth term test for divergence? It does. This, if I take the limit of this sequence as n goes to infinity, this equals 0. That just tells us we have to run another test. Okay, so now I'm going to compare and let f of x equal 1 over x plus 2 squared. And all my work moving forward will be done with this function. And the first thing I want to do is make sure that I can even use the test. So I have to think about my conditions. Are these positive? Yes, this function will always be positive. So f of x is greater than 0, especially for x greater than or equal to 1. Is it continuous for x greater than or equal to 1? Well, the only place this is not continuous is at -2, so it definitely would be continuous for everything past 1. And then the third thing, is it decreasing? And yes, this is where the FRQ would probably tell you it's decreasing. I would just make sure you state it. So 3 f of x is decreasing for x greater than or equal to 1. That means we can use the integral test. Let's do it. So we're going to do the integral from 1 to infinity of 1 over x plus 2 squared. I'm going to do some u substitution. So u is x plus 2. du is dx. Yeah, see, I have a notation error on my thing here. Kind of mad at myself, but hopefully you guys will forgive me. At least I'll do it correctly now for you guys. Okay, so now I'm going to have the limit as b goes to infinity from 1 to b. In fact, it's not going to be 1 to b. It's going to be, let's see, since I'm changing these to u values, if x is 1, then u is 3. And if x is b, then u is b plus 2. And it's going to be 1 over u squared du. So u to the negative second du. Now I need to integrate. So negative u to the negative first. So negative 1 over u. We're getting there. Plug in b plus 2. Minus negative 1/3. Now I plug in infinity here, and I'm going to have 1 over infinity. So that's 0. So this whole limit would just be 1/3. That first term would 0 out. We'd get 1/3. So here's some things to understand. What that means is this improper integral converges. That means the original series converges. However, it doesn't necessarily mean that it converges to 1/3. Like this just tells us that that integral converges. That integral and that series are not exactly one and the same in terms of their values. So all we know is that the series will also converge. We do not know if it will converge to 1/3. So this converges. Therefore, the series from n equals 1 to infinity of 1 over n plus 2 squared converges by the integral test. We having fun yet? Absolutely. Nice. Woo! All right. What about the next one? Emery, tell me what your thoughts would be on this one. What do you think? What would you do?
Start off by determining whether it's positive. That's one.
Is it?
Yeah.
Okay. Then what?
Then checking if it's continuous.
Is it?
Yeah.
Okay. Then what?
And then making sure it decreases.
Okay. Is it?
Yeah.
Okay. So then onward to the integral test, huh? You are wasting a lot of time.
I'm very good at making sure.
Josh, why are you shaking your head? Yeah. If we look at the limit of this sequence as n goes to infinity, since those degrees are the same, this equals 1/2, which is not 0. Like these terms, if you're going to be adding up a whole bunch of terms, and those terms are never approaching 0, which means this series never has a chance to converge. Don't be a time waster. I'm glad you said all that though. Like, I'm really happy that that happens. Not for any like making fun of you, but I just to like hit that point home in your head. That always look for this. So this diverges by the nth term test. So that's a good thing when that happens. It's a beautiful thing. No work to do. All right. For this next one, I'm going to put the key up instead of, that way I can kind of talk through it It's a very similar problem. But there's one little wrinkle that I want to talk through because it was what I was talking about right at the beginning of the notes. Okay. So just don't write anything just yet. I just want you to listen. So on this one, it's all the same setup. We let f equal 2x over 3x squared plus 4. They're positive for x greater than or equal to 1. It's continuous for x greater than or equal to 1. Then look what happens if you go through and look and see if it is decreasing. So you do the quotient rule, you find your critical numbers, and the critical numbers turn out to be plus or minus 1.155. And if you plug in a number past 1.155, then f prime is negative. What that means is from 1 to 1.155, the function is increasing. I think it would be positive. I didn't actually check that. But that was what I was talking about at the very beginning. You know, just because the test says it has to be true for x greater than or equal to 1, that's not necessarily true. It just has to eventually be true. And so that's what happens on this one here. And we know for sure f of x is decreasing for x is greater than or equal to 2 with 100% certainty. And so we can still apply the test. That was the only reason I have this example. You could write it down or not. Everything else is the exact same on this problem, but that was just something I wanted to talk about. Take a picture or whatever. That's up to you. Aside from that little thing, there's nothing different between this and the first example that we did. So that ends my least favorite test. You guys ready for my favorite test? The P-series test. Very similar to the harmonic stuff that we talked about last time where I showed those videos. So first, you need a very basic looking series. And the two most basic looking series are your geometric series and your P-series. And make sure you don't confuse how the two look, okay? So how this will look is if you have a series from 1 over n to some power, and that's all you have, 1 over n to some power, then this series will converge if that power is greater than 1. You know, last time we talked about if you had 1 over n, this series diverges. That's the harmonic series. I showed you guys a YouTube video proof, and I showed you guys my little intuitive proof of writing out those two strings of series. The harmonic series diverges. So if P is greater than 1, even if it was 1.01, if you took 1 over n to the 1.01 power, that series will converge. So any power above 1, it will converge. If your power, if that exponent is between 0 and 1, including 1, then it will diverge. And so that's really all we're checking for is that exponent. Is it bigger than 1 or is it less than 1? It's really all we're after. And so if you know the harmonic series diverges, if you can just remember that, then you're in pretty good shape for this. So it says determine if the following series converge or diverge. So I have the sum of 1 over n cubed from 1 to infinity. This is a P-series test. All I'm doing is looking at that exponent. If it's greater than 1, this series converges. I don't know what it converges to, but I know that this converges because P is 3. This one converges. P is greater than 1. How nice is that? The next one. So we just have to be careful that we know how to deal with radicals and convert them to exponents, but this is the same as n to the 1/2. So 1/2 is definitely between 0 and 1. So it diverges. Such a stark contrast between the integral test and the P-series test. The next one, 5/2, is definitely above 1. So this one converges. So the easiest test we can use, you just need to make sure you don't flip these things, because then you miss them. The next one is n to the 1/5, which is definitely between 0 and 1. So diverges. Now this one's interesting because we have to think about what that series would be. We had to turn this into kind of like a little formula here. I want you guys to practice that. I want you guys to write this in sigma notation. I want you to write the sigma, the summation notation that represents this particular series, because we will have to do some of that. There's mine. Be 1 over the cube root of n squared. And you can check it. Once you guys write your formula, just plug in the bottom number and make sure it generates the first couple of terms. If I plug 1 in for n, I'm going to get 1. If I plug 2 in for n, I'm going to get 1 over a cube root of 4. If I plug 3 in for n, and so on. So these things, for some students, I remember in college, this was really hard for me. I struggled turning sequences or series into an actual notation like this. But anyway, so this is n to the 2/3. Remember, it's power over root. Don't mix that, because then you would get 3/2 and you would say it converges, but it's power over root. So this is the same as n to the 2/3 power. So it diverges. P is 2/3. What you yahoos think? So we've learned half of our tests. We've learned nth term, geometric, integral, p-series test. In the e-learning video for Wednesday, you'll learn direct comparison test and limit comparison test. Then I think we learn alternating series. I am not sure, but yes. And then the ratio. All right, we're done. You guys have an assignment. I will publish the e-learning page. So that just needs to be done by Friday. All right, you guys are free to go. Peace out, homie.
Okay.
You too.